Hi guys, welcome to a new video. Okay, on this opportunity we want to resolve this problem. We have a uniform spherical ball of mass m rolling without slipping down a wedge of mass m and angle alpha, which itself can slide without friction on a horizontal table. This system moves in the plane shown in the figure, and g denotes the acceleration of the gravity. First, we want to find the Lagrangian and the equation of motion for this system, and second, for the special case when the mass of the wedge is equal to the mass of the ball and alpha is p², we want to find the acceleration of the wedge and the acceleration of the ball relative to the wedge. Okay guys, let's have a solution for this problem. We have here a free body diagram with the ball. Here we have the velocity along the y-axis. We are calling y-axis the axis along which the ball rolls. Then Vy is the velocity of the center of mass of the ball, and the horizontal and vertical components of the velocity are Vy cosine of alpha and Vy sine of alpha respectively. This angle alpha is the angle of the inclination of the wedge, right? This angle is a alternate interior angle with the angle alpha of the inclination of the wedge. So the components of the velocity are Vy cosine of alpha and Vy sine of alpha, as we said. If we want to write those components, we have Vx equal to x dot plus y dot cosine of alpha. This is the horizontal component of the velocity of the system. Okay, this x dot is the velocity of the wedge, and this y dot cosine of alpha is the horizontal component for the center of mass of the ball. If we go to the figure again, we can see that the wedge is moving to the left, right? The ball is moving down the wedge, rolling down, and as we said, it has two components given by Vy cosine of alpha and Vy sine of alpha. So we know that x dot is equal to the derivative with respect to the time of x, and y dot is equal to the derivative with respect to the time of y. And the velocity of the system ball wedge is equal to the vertical component is equal to y dot sine of alpha. Okay, here we don't have vertical component of the wedge because the wedge is moving just horizontally, right, along the plane, horizontal plane. So we only have the component of the ball as the component of the system for the vertical component. Okay guys, we want to know the velocity of the system. So we know that the velocity of the system is going to be v, and v squared is going to be vx squared plus vy squared. Okay, so we want to to find the square velocity, we want to find first Vs squared and Vy squared. So Vx squared is going to be, we know that Vx squared is given by this. Then we have x dot plus y dot cosine of alpha squared, right? So we want to use the perfect square formula given by this equation. We already know this. Okay, when we use the perfect square formula, we get v squared is equal to the first term square plus the second term square plus 2 times the first term multiplying the second term. And that's Vx squared. Now we want to calculate Vy squared. Vy squared is, we know that Vy is given by this formula. Then Vy squared is going to be y dot squared sine square of alpha, because v squared is equal to vx squared plus vy squared. We are gonna replace those vx and vy squared into this square velocity formula to get the following. V squared is equal to x dot squared plus y dot squared cosine squared of alpha plus 2x dot y dot cosine of alpha plus y dot square sine of alpha square. What I did is I replaced x dot squared and y dot squared into the formula for v squared. I'm gonna highlight y dot squared and cosine of alpha and y dot squared sine of alpha. I'm highlighting those terms because they are similar. I take from common factor y dot squared out of the highlighted terms, and we get v squared equal to x dot squared plus y dot squared. So common factor of cosine squared of alpha plus sine squared of alpha plus 2x dot y dot cosine of alpha. And because the relationship of this trigonometric relation, we have that this is equal to 1, right? Cosine squared of the angle plus sine squared of the angle is equal to 1. And finally, the velocity squared of the system is equal to x dot squared plus y dot squared plus 2x squared y squared cosine of alpha. And we call this equation number 1. Now we want to calculate the kinetic energies for the ball and the wedge. These kinetic energies are given by, first, the kinetic energy for the ball is T for the ball is equal to 1/2 of the mass, the velocity of the ball square. We know that that's the velocity of the center of mass, plus 1/2 of the moment of inertia multiplying the velocity square, the rotational velocity or angular velocity, right? Because we have to have here the composition, the rotational kinetic energy and the translational kinetic energy. Because the ball is moving, is translating, but at the same time is rolling, okay? But because we have a solid sphere, the moment of inertia for a solid sphere is 2/5 of the mass multiplying the radio square, okay? Then the kinetic energy for the ball is going to be 1/2 of the mass, the velocity of the center of mass square, plus 1/2. Okay, we know for this case the moment of inertia is 2/5 the mass multiplying the radius square. Okay, W square. All right. The relationship between V and omega is this, but V is equal omega R. When a body is moving with a rotational motion, the relationship between the translational and rotational motion is given by this equation. V is equal to omega squared. Sorry, V is equal to omega R. Then omega is equal to V dividing R. Okay? Then omega squared is V squared dividing R squared. I will replace this right here into this to get the following. Okay? Replacing the omega squared, we get this. We need to cancel some terms. These two cancels with these two out. This R squared cancels with this R squared. Then we get for the kinetic energy of the ball 1/2 of the mass V squared plus this would be 1/5 of the mass V squared, and that's equal to 7 times mass V squared. Then the kinetic energy for the ball is equal to 7 times mv squared. Let's call this equation equation number 2. Okay, now we want to calculate the kinetic energy for the wedge. The kinetic energy for the wedge is equal 1/2 mass of the wedge plus mass of the ball multiplying the velocity of the wedge squared. Okay, this is the total mass because the whole thing is moving together. I mean, the wedge is moving to the left according to the illustration of the problem, as you can see here on the figure. Okay, but remember, the wedge is not moving by itself. The wedge has the ball on top. The ball is on top of the wedge. So we have to take into consideration the mass of the ball. Then the kinetic energy of the wedge includes the mass of the ball. Okay, because the whole thing is moving together. Then, because of this situation, the kinetic energy of the wedge is going to be 1/2 of the mass of the wedge plus the mass of the ball multiplying the velocity squared. Okay, we call this equation equation number 3. Then the kinetic energy of the system the kinetic energy of the system is kinetic energy of the wedge plus kinetic energy of the ball. This system is equal to kinetic energy of the ball 7 times mass velocity squared plus 1/2 mass of the wedge, mass of the ball, x dot square. We remember that according to equation 1, the velocity of the ball is given by this expression. We replace this velocity squared into the last formula we wrote, and we get the following equation. Kinetic energy of the system is equal to 7 times mass of the ball. Okay, we know velocity squared according to equation number 1. S dot square plus y dot square plus 2x dot y dot cosine of alpha. Okay, now 1/2 of the mass of the wedge plus the mass of the ball, s dot square. Let's call this equation equation number 5. The potential energy for the system is the same as the potential energy for the ball, and is given by the following equation. V of the system is equal to the potential energy of the ball, and this is equal to minus mg y sine of alpha. Let's call this equation equation number 6. Why the potential energy of the system is equal to the potential energy of the ball? Okay, we consider the potential energy of the wedge as 0 because its dimensions are not taken into consideration. That means that we are treating the wedge as a punctual particle, right? Then, because we are treating the wedge as a particle, we are not taking its dimensions into consideration. That's why we only take into consideration the potential energy of the ball, but this is mgy sine of theta. Why is minus? Because let's go to the illustration of the problem. If we see the illustration of the problem, we see here that y is the axis along which the ball is rolling, and the vertical component is this, right? And the horizontal component of this position is this. And obviously this height is y. Okay, this is the angle alpha. We know this alpha. They are internal alternate angles, right? And this is y sine of alpha. This is the opposite angle or the opposite side to this angle, okay? So that's why we are taking that as the vertical component of the coordinate. And because we are taking the horizontal table as the origin of reference, and because the particle, no, we take this here, sorry. We take the horizontal, we take the reference on top, right here. Then the potential energy is negative. If the potential energy, we are taking the vertical component below the origin of coordinates of the reference, or potential energy is negative. If we take it above, it's positive, but we are taking it below, then it's negative, right? So let's come back to the problem. Okay, now we want to calculate the Lagrangian of the system. As we know, the Lagrangian of the system is the function that is the difference between the kinetic energy and the potential, right? So the kinetic energy is, as we know from equation number 5, is equal to 10 to 7 tenths mass multiplying x dot squared plus y dot squared plus 2x dot y dot cosine of alpha plus 1/2 of the mass of the wedge plus the mass of the ball multiplying x dot squared. Right? This is going to be minus the potential energy of the system, that is minus mg sine of alpha. Okay, remember this is minus, and minus is plus. Then the Lagrangian of the system is going to be the following equation. What I did is to rewrite the equation of the Lagrangian. So taking into consideration that minus and minus is plus, and rewriting the equation. So the Lagrange equations for this is a system with two generalized coordinates. So this is a system with two freedom degrees, or two generalized coordinates to represent the system. Okay, so the Lagrange equations are the Lagrange equations are for each generalized coordinate x and y the following equations. Derivative with respect to time, dl dx dot minus dl dx equals 0. And derivative with respect to time of dl dy dot minus dl dy equals 0. Okay, so let's work with these equations. These are the Lagrange equations, and remember the generalized coordinates for this system are x and y. So we have to have the same number of equations as the generalized coordinates for this system, okay? Then let's calculate dl dx dot first. Let's work with the s coordinate first. So we are calculating dl dx, and that's equal to, okay, let's go to the Lagrangian real fast. 7 tenths. Okay, we are calculating the derivative with respect to x dot. So we because we are calculating the derivatives with respect x dot, the last term, this term, mgy sine of alpha is going to be 0. The derivatives with respect x dot, okay? And the derivative with respect x dot of x dot squared is going to be 2x dot squared. The derivative of y dot squared is going to be 0. And the derivative of this term, 2x dot y dot cosine of alpha, is going to be 2 y dot cosine of alpha. And this term is going to be 1/2 of the mass plus the other mass multiplying 2x dot, okay? So it's the derivative of this term with respect s dot. It's going to be 7/10 of the mass. Okay, the derivative of s dot squared is 2x dot, okay? And the derivative of y dot squared is going to be 0, okay? Then the derivative of 2x dot y dot is going to be 2 y dot cosine of alpha, okay? Plus the derivative of the term containing the two masses and the x dot squared. That derivative is going to be 1/2 of the mass plus the mass of the ball. Okay, the derivative of s dot squared is 2x dot. The derivative of the last term of the Lagrangian is 0. With respect to this variable is 0. Okay, so let's go and do some simplification here. So we can simplify this 10 with this 2 and 2, and we can simplify this 2 with this 2 as well. Doing that simplification, we get the following equation. So we got that equation, okay? If we take the, so what we did is this part, dl dx dot, okay? Now we want to take the derivative with respect to the time of dl dx dot, okay? So the derivative with respect to the time of this expression would be derivative with respect to the time of dl dx dot is equal to 7/5 mass. Okay, the derivative with respect to the time of x dot is going to be x2 dots plus the derivative with respect to the time of y dot is y2 dots cosine of alpha. Okay, we don't take the derivative with respect to the time of cosine of alpha because alpha is constant, okay? Plus n plus m s2 dots, as we already know. Okay, guys, this is the first part of the Lagrange equation for the x coordinate, all right? So let's go and see the second part of the equation is dl dx, okay? But we check the Lagrangian, and the Lagrangian doesn't depend on the variable x at all. So the derivative of the Lagrangian with respect x is equal to 0 because no x term is in this equation. Then we have dl dx is equal to 0. Okay, all right, so let's go and see how the first Lagrange equation of motion is going to be. Basically, we know that dl dx, the derivative with respect to the time of dl dx minus dl, okay, dl dx dot minus dl dx is equal to 0. Okay, Because dl dx is 0, we only have this part for the Lagrange equation, the highlighted part. So basically that's the Lagrange equation for the x coordinate. So let's rewrite it on the next page, and we will get the following. This is the Lagrange equation for the first Lagrange equation, okay? Okay, for the x component of the system. Okay, we can see here that we have the s component and the y component as well on the final result. So this is a equation that contains two terms, or the two variables. And let's call this equation equation number 7. What I did here is basically I wrote the same last equation, but I distributed the 7/5 into the parentheses with the mass and the other terms, as is a procedure that is really easy, okay? So that's equation number 7, and it's the result for the Lagrange equation for the x component of the system. Now let's work with the y component. All right, so the derivative with respect to y dot is dl dy dot of the Lagrangian. If we check the Lagrangian real fast, so the derivative of x dot squared is going to be 0. The derivative of y dot squared is going to be 2y dot. The derivative of 2x dot y dot cosine of alpha is going to be 2x dot cosine of alpha. The derivative of this term, m plus n x dot squared, is going to be 0. And the derivative of mg sine of alpha is going to be mg sine of alpha without the y, okay? Because it's the derivative. Oh, sorry, the derivative is going to be 0 of this whole term because we are derivating with respect to s dot. Sorry, y dot. Okay, so let's go write the derivative with respect y dot of the Lagrangian. Then we have dl dy dot is equal to 7/10 of the mass. Okay, as we know, the derivative of x dot squared is 0, the derivative of y dot squared is 2y dot, plus the derivative of the next term, x dot 2x dot y dot cosine of alpha is 2x dot cosine of alpha. Okay, we can simplify this 10 with this 2 and 2, and finally we get 7/5 of the mass y dot plus s dot cosine of alpha. Okay, then the derivative with respect to time of this term is derivative with respect to time of dl dy dot is equal to, it's pretty easy, okay, is 7/5 of the mass. Okay, it's the derivative with respect to time is y2 dots plus, okay, x2 dots cosine of alpha. Okay, the next part would be calculating dl dy. Okay, dl dy. So dl dy is equal to, okay, let's go. the Lagrangian dl dy. Let's see the Lagrangian. All these terms, x dot, y dot, x dot, y dot, x dot square, are zero, the derivative with respect to y. The only term that is surviving here is mg y sine of alpha. Then the derivative with respect to y of that term is mg sine of alpha, okay? So, dl dy is mg sine of alpha. Okay? Then let's write the Lagrange equation. The Lagrange equation. Okay, the Lagrange equation would be derivative with respect to time dl dy minus dl dy. Okay, dl dy dot minus dl dy equals 0. And this is this. 7/5 of the mass multiplying x y dot square. Okay, I'm gonna distribute this, time this, and this into the parentheses, okay? And that's gonna be y dot is y2 dots plus 7/5 of the mass x2 dots cosine of alpha minus mg sine of alpha equal to 0. Let's call that equation number 8, and that is the second Lagrange equation of motion. So this is the part 8 of the problem. This is the part 8 of the problem, guys. The Lagrange equations of this problem, okay? On the next video, we are gonna calculate the second part of this problem, the part B. All right, so see you on the next video calculating the part B of the problem, and thank you for watching. Please don't forget to subscribe to my channel. Don't forget to share this content, this video, and don't forget to give me a thumb up and a like. Okay guys, see you on the next video doing the second part. Bye.